is okay. Professor Kalai is currently affiliated with Einstein Institute of Mathematics, Hebrew University, and F.E. Arazi School of Computer Sciences, Richmond University at Herzliya. Professor Kalai has been the recipient of the Polya Prize in 1992. He also won the Erdos Prize by the Israel Mathematical Society in 1993. Moreover, he has won the prize of Fulkerson Prize in 1994. Uh, Professor Kalai is known for finding various variants related to simplex algorithm, linear programming that can be proven to run the sub-exponential time for showing that every monotone property of graphs has a sharp phase transition for solving Borsuk's problem, which is a very famous Borsuk conjecture. And other than that, a lot of theories has been developed by Professor Kalai, and probably he in the area of combinatorial commutative algebra. He is known due to his conjecture, which is named after his name, Kalai's conjecture. And moreover, he has worked on various problems, including Hirsch conjecture, convex polytop, and polyhedral combinatorics more generally. Moreover, Professor Kalai has been one of the invited speaker of the International Congress of Mathematics, which was held last time in 2018 in Rio de Janeiro. And now it's time. I will not take much time. Now over to you, Professor Kalai.
Oh, thank you very much. This is really a pleasure and an honor to be invited to talk in Lahore and in a seminar having the name of John Conway. And so here is again the poster of the lecture. And maybe I will just mention where I gave a similar talk in CERN a few years ago, and I mentioned that CERN was established more or less at the time where I was born. You can see here my parents and me and my sister. And this kind of cooperation after the Second World War was a way of healing Europe, and it had a lot of it led to a lot of progress, both scientific and otherwise. And one thing that probably you didn't know is that there is an amazing scientific partnership between Jordan, Cyprus, Egypt, Iran, Israel, Pakistan, and the Palestinian Authority in Turkey. And this is an accelerator called Sesame. This is actually an acronym that was opened in Jordan 2017. So I hope that I will also talk in all these other countries, and also that perhaps I will do it face to face and not only by Zoom when the pandemic will be over. So this gives hope to the young generation, like my grandchildren here. And the picture of the person you see, Eliezer Rabinovich, he was one of the founders of Sesame, and just a few days ago he was appointed to the president of CERN for a term. So this is an opportunity to congratulate him. And just my last slide before I go to the talk is that this is a picture of, this is a good friend of mine, Janos Pach, who actually visited Lahore a few years ago and gave a lecture. I don't know if any of you attended the Janos lecture, but he's a great speaker, and so I hope to follow his so in some sense I follow Janos' footsteps, but it would be nice to do it in person. So I was told that I'm one of the early Israeli speakers in the seminar, and it's nice to, right now I am in New York, but perhaps some of my colleagues from Israel are also attending, so if they are, maybe I will ask them to say hi, so you will have actually a genuine voice from Israel. And as this seminar is named after John Conway, that passed away a short time ago, and here is a very nice attribute by XKCD, which is a very nice site. Well, actually, oops, sorry. Yeah. So this is based on his famous life. I can tell you a very quick memory from John Conway. I met him several times, and perhaps the most meaningful meeting with John Conway was in 1979. I was visiting Cambridge. I was fairly young then. And we sat in the common room. This is not the building, the current building of mathematics. This was a building of mathematics, I think, and statistics. And yeah, he offered me to sit with him, and he told me a lot of things. And he also showed me some game which was called football. Later, I learned how to spell it, and he offered me to play, and I played, and very soon I was losing. So he said, you know, every time you feel you're losing, we can change sides. And indeed, every time I felt that I'm losing, we changed sides. And then a short time afterwards, I still felt that I'm losing. And it was very nice. And on the way, he also talked with me about mathematics, and also with several other people in parallel. I think even his wife then was in the room. And he also showed me this book, Winning Ways. It didn't exist yet in this form, but it was a big printed pile of printed pages. He offered me to take it to my hotel for one day and to read it. I said this would be too much for me, so I didn't, and I only read the book years later. And yeah, he was undoubtedly an amazing person. So now let me go on to the overview. So for some reason, some parts of the Zoom are covering. Okay, so it is a serious possibility that quantum computers are not possible. So our world is a world devoid of quantum computers. And this is what I expect, and I've been studying this possibility since 2005. And recent claims about quantum supremacy or quantum advantage, starting with Google's 2019 announcement, are in tension with my theory. And we need to carefully study these claims. I'll mention them briefly. And in principle, failure of quantum computers have a variety of consequences. It's also related to very interesting mathematics, even combinatorics. And here we will briefly discuss some connection with classical problems in philosophy. So here is, in brief, the argument against a quantum computer. Noisy intermediate scale quantum systems, in particular noisy intermediate scale quantum computers, they are called NISQ systems, represent a low level. So the argument is basically a computational complexity argument. Noisy intermediate scale quantum systems represent a low level computational ability. And this low level computational ability will not allow using them for building quantum error correcting codes that are needed for quantum computation. So this is the crux of the matter. Because the intermediate scale quantum systems are so primitive computationally, this show that, or this, I wouldn't say show, but this implies that you will not be able to reduce the noise level to make these systems do wonderful computation, and in particular to build the error correcting codes that are needed for quantum computing in a larger scale. And now let me tell you about two problems, philosophical problems that people were thinking about since ancient times. probably in many cultures, because these are very, very natural problems. We have records, certainly we have records from Greek philosophy. And the question is, okay, they didn't think about quantum systems, but the question we can ask is, can we predict the future of complex quantum systems in nature? And for that, we can think in parallel about two examples. One is the Sycamore quantum computer with 12 qubits. Sycamore is a computer which was built in Google. I'll mention it in a minute. And 12 qubits is the smallest number of qubits in the famous Google experiment. And the other example is Alice, a human being whose decisions and free will are in question. And we can ask, can we build a device, M of S, that predicts the behavior of Sycamore? We can distinguish between deterministic behavior. Actually, Sycamore produce samples. Can we build a device that predicts precisely the sample, or we can relax a little bit the condition and ask, can we build a device that predicts the samples probabilistically? And the second question is, can we build a device, this device I call M of A, that predicts the behavior of Alice or the decisions of Alice? And my answer is to both questions is negative. The answer is no. The free will versus determinism problem is the question how to reconcile the apparent fact that on the one hand, people have free will, namely the free decision affects their future. The decision we make now are based on our thought process, and they are determined now. We can choose between several futures. We have several futures to choose between, and we make the choice freely, at least partially freely, in our conscious. On the other hand, the mathematical laws of physics are deterministic. And my answer is that the ambiguity is not in the mathematical law of physics, but there is an ambiguity in the way the future is determined by the past, not in terms of the mathematical laws of physics, which are fully deterministic, but in terms, even in the quantum case, but in terms of the physical description of the object we discussed. This is where we have ambiguity. And we need to separate between claims about the future that belong to the causal fabric of the past and the future, and the claims that don't belong to this fabric. And these answers are related to many suggestions over the years, but the fact that the world is devoid of quantum computers as a matter of principle is a new ingredient in this argument. Okay, and now we'll start the actual lecture with part one, which is background. I will not be able to give full background, so but I hope this will ring a bell with you. And the first thing to remember is the notion of computers or Boolean circuits. This is the model I chose. And we can think about the basic memory component in classical computing as a bit, which can be in two states, 0 and 1. And a computer or a circuit has n bits, and it can perform certain logical operations on them. The NOT gate acting on a single bit, which flips the value of the bit, and the AND gate acting on 2 bits. And these two gates, these two simple gates, suffice for the full power of classical computing. And if you don't care about efficient computation, namely a computation that involve only a polynomial number of gates in terms of the input, then they certainly suffice for the full notion of computation in nature. If you restrict yourself to efficient computation, which was a development from the 70s, then comes a distinction between classical computing and quantum computing. And now I will give you in one slide a description of what is a quantum, what are quantum computers, and again, if you're not familiar with it, this will just be a taste. A qubit, which is the quantum piece of memory, is is this time it also has states, but not only two states, it has a continuum number of states, and the state of the qubit is a unit vector in a two-dimensional complex Hilbert space. Now, if you have a quantum computer with n qubits, then the state of the computer is a unit vector in a 2 to the n dimensional vector space, which is the tensor power, the tensor product of all the two-dimensional Hilbert spaces, which correspond to the individual qubits. And then, like in the case of quantum circuits, gates are unitary, we have gates. And in this case, gates are unitary transformations. And we can put 1 or 2 qubits through gates representing unitary transformation acting on the corresponding 2 or 4-dimensional Hilbert space. Of course, we can think theoretically about a unitary transformation that acts on the entire 2 to the n-dimensional space, but we don't expect that implementing such a unitary transformation would be physical. What we expect that in any physics known to us, we will apply operation only locally on a small number of gates. And it turns out that if we restrict ourselves to small number of gates, like in the case of classical computing, there is a small list of gates which is sufficient for the full power of quantum computing. So if you look at the quantum computer of IBM or the quantum computer of Google and many other companies, you see such a list of gates. In IBM, you have even a few extra gates to make computation easier, but they suffice to the full power of quantum computing. And now I have to tell you one more ingredient, which is what you do at the end of the computation. And then what you can do is measure the state of the qubit, and measuring the state of the qubit give you move you from a unit vector in k-dimensional Hilbert space to a probability distribution on 0, 1 vectors of length scale. So what you get at the end is a sample, is a 0, 1 vector of length scale. So this is the description of quantum computer. Here is a very brief, just a picture of our computational complexity world, where I mentioned 3 computational tasks that I will mention. So the yellow circle, the yellow small circles, I hope you all see, this corresponds to polynomial time computation. This is, in the idealized way, this is what we can expect to do with classical computers, polynomial time computation. And you can also see the important class NP, which is not, which stands for the name non-deterministic polynomial time. This is a much larger class of computational problems, and we don't believe that computers can efficiently solve such problems, not even quantum computers. So this is one of the great discoveries in the 70s, is that there are problems very simple to state, and when you know the answer, very simple to check, that we don't expect that there will be an efficient algorithm, even with quantum computers, though some people hope. And this is the class NP. Of course, the fact that NP is not equal to P, it's widely believed, it's probably correct, but it is a mathematical conjecture. Nobody knows how to prove it, and there are a lot to be said about that. There is a very similar class, co-NP. I will not define it, it's sort of a dual class. And there are problems which are both in NP and in co-NP, like the problem of factoring an integer to its prime factors. And the problem of factoring is not believed to be in P. The best algorithms are exponential. This is notoriously difficult problem. All our crypto systems, or most of our crypto systems, are based on the fact that factoring is difficult. And on the other hand, the famous algorithm of Peter Shor showed that factoring can be performed efficiently with a quantum computer. You can see here NP and co-NP are part of a hierarchy of a complexity class, which is called the polynomial hierarchy. This is called PH in this picture. And the power of quantum computers, for all we know, extend also over to problems which are beyond the polynomial hierarchy. And one such problem, it's a sampling problem that I'll mention later, is called Boson sampling. And here is a third algorithmic problem, which is indicated in the slide, is to compute permanent of matrices. So you may know, and this is one of the miracles of the world, that determinants for n by n matrices can be computed efficiently by Gauss elimination algorithm. But for all we know, permanents are hard to compute. And this is a very hard computational problem, which extends beyond the polynomial hierarchy, and for all we believe, also beyond the power of quantum computers. But this is a problem to keep in mind. And you know, permanents are really a lovely objects. Okay, now NISQ circuit, or noisy intermediate scale quantum computer, are simply noisy quantum circuits with at most 200 qubits or 500. You can put the bar as you wish. They have some qualitative, this look a little bit arbitrary, but I should say they have some qualitative properties which distinguish them from high-scale quantum computers. For example, they don't allow, it's too few qubits to allow for quantum fault tolerance so this is an important regime. In some sense, in some not very accurate sense, if you have a computation and you want it to perform well, you have to make sure that no component, no gate is faulty. A single error cause your computation to fail. So this is what distinguishes NISQ system. Okay, so this is really actually a slide that I presented in CERN in August 2019, except the boldface red part. And this is a near-term task for NISQ devices. So the first goal is to demonstrate what's called quantum supremacy or quantum advantage or huge quantum advantage via systems of non-interacting bosons. And I mentioned also a baby goal, which is to do it even for 10 bosons, to give an accurate boson sampling distribution. The second goal is to demonstrate quantum supremacy. Again, I'll come to it in a minute, on random circuits, namely circuits that are based on randomly choosing the computation process in advance with 50 to 100 qubits. And a baby goal is to show good such computers with 10 to 30 qubits. And the third goal is to create what's called the distance 5 surface code. And this requires a little over 100 qubits. In any case, the important thing is to build a good quality quantum error correcting code. And the baby goal would be to do a distance 3 surface code. And goal 3 is still fairly remote, but what happened a few months after I gave this talk, actually, it was a nice story. I started hearing some hints that maybe the Google team is going to announce this achieving quantum supremacy soon. And then I met in a conference in Jerusalem, a very great quantum computation theorist and mathematician, Thomas Wittig, and told me, you know, Gil, actually there is now a paper by Google that announce quantum supremacy. And actually, a few days later, the paper was leaked somehow, and then a month later, it was published. And so the task of having quantum supremacy, achieving some computation that classical computer cannot achieve, was achieved by a team from Google, was claimed by a team for Google in 2019. A year later, a team from USTC claimed to demonstrate quantum supremacy on a system of non-interacting bosons. Google claimed that it will require 10,000 years for a classical supercomputer to achieve what they managed to do in 2,200 seconds, and the group from USTC claimed that it will take 2.5 billion years for a classical supercomputer to achieve what they have done also in 200 seconds. And what I predicted that both goal 1 and 2 and 3 are impossible, will not be achieved at all, not to say in few months. And the baby goals will already demonstrate difficulties that will come to play in the fact that the more ambitious goals will not be achieved. So at least it looks that the claims in 2019 and 2020 are in serious tension or even falsify my prediction. So let me tell you a little bit about the Sycamore computer. It's a name of quantum computer developed by a team from Google. In 2019, it was announced that quantum supremacy was achieved via a sample of few million bit string of length 53. And here is, you can see the picture, quantum supremacy using programmable superconducting process. It appeared in Nature. Okay, so how do we look carefully? How do we put this supremacy or advantage claims under scrutiny? So we have two passes to go. Of course, an important thing to do is to replicate by other groups what these groups are claiming to do. There are various other groups that can do similar thing. It can even be on smaller systems, just to show that these claims are reproducible, which is the ultimate test for a scientific discovery. But two things that can be done is, the first is, can we spoof the experimental claims for supremacy advantage by better classical algorithm? So, you know, if a group claims that it will take 10,000 years on a supercomputer, can we reduce this number? And indeed, few days after the Google paper appeared, a team from IBM managed to reduce the number for 10,000 years to 2 days on a very powerful supercomputer. And later, another team, several other teams managed to find better and better classical algorithms. So now it's not considered so difficult to do what Google claimed they were doing. And the second question, which is also important, is, are the experimental claims reliable? You have to look into the claims are essentially statistical claims, and you have to look at the statistical reasoning and the data, and to check, like in any major experiment, to check if the statistical reasoning and the data are reliable. And indeed, I'm involved in the long-term project to test the statistical aspects of the quantum supremacy demonstration. The first paper by me, Yossi Rinot, and Tomer Shoam is now in press in Statistical Science. And we examine, also raise some concerns on some aspects of the statistical study, also have some praises for this statistical study of the Sycamore experiment. And I should say this is my second paper in statistical science. 22 years ago, I published the paper with three other colleagues, McKay, Bar Natan, and Bar Hillel, which examine another, I would say, far-reaching claim, and test the statistical claim. And in some, I should say, surprisingly, there are some similarities, many yet to be explored, between these two cases. Okay, so let me mention now that my analysis of quantum computers, especially since 2014, is based on a theory which was developed by me with Oded Schramm and with Itai Binyamini and Oded Schramm of noise sensitivity and noise stability of Boolean functions. And this go back even to earlier paper with Kahn and Lineal. And here we are, me with Oded and Itai in the top picture. And this is a very recommended, I will not get much into the theory, but this is a very recommended book about this theory by Garban and Steif. And this theory involves Fourier analysis, Fourier methods. Again, there is a very good book by Ryan O'Donnell on analysis of Boolean function, and implement it for Boolean for quantum systems was carried out in a paper with Guy Kindler that you can see in the bottom picture in 2014. And I will now mention a little bit about my work with Guy Kindler. So I mentioned already, but I didn't elaborate about the model of Boson sampling. And these models first appeared in the literature in a paper of Troyansky and Tishby, with Dror Troyansky and Naftali Tishby from 1996. And then it was introduced again and much studied in important papers by Aronson and Arkhipov from 2010 and 2013. And the algorithmic problem is fairly simple to state. Given a complex n by m matrix X with orthonormal rows, you sample subsets of columns with repetitions according to the absolute value squared of the permanence. And this task is referred to as Boson sampling. And as I mentioned, computing permanence is very difficult computational task, even for quantum computers. But sampling according to the absolute value square of permanence is easy for quantum computers. Quantum computer can perform Boson sampling on the nose. And this is essentially goes back to Troyansky and Tishby. And there is good theoretical argument by Aronson and Arkhipov that these tasks are beyond reach for classical computers. So in some sense, if classical computers can do, so they are beyond. They are, and this is really one of the strong theoretical argument, computational theoretical argument for the advantage of ideal quantum computers. So here is just an example to demonstrate what is Boson sampling. You have a matrix. In this case, it's 1 over square root 3, I over square root 3, 1 over square root 3, 0, 1 over square root 2, and I over square root 2. This is the input matrix. And now you consider pairs of columns. For example, the first and the third column. Compute the permanence. So permanence is the same as determinant, but without the sign. Take the absolute value, square it, and this gives you a probability. So for 1 and 3, the probability you get is 1/6. So here we get 6 probabilities. 2 of them are 0. And these probabilities, and now you sample the pairs of columns according to these probabilities. And lo and behold, quantum computer can do it. There is an analog computational task, which is called Fernum Sampling, where you compute determinant rather than a permanent. And there, of course, if you repeat the same column twice, you get 0. This is a famous law in mathematics. Also, it's related to Pauli exclusion principle in physics. And then you get these 3 probabilities. Okay, so now we know what is a Boson sampling. And now let's move to my argument, the second part of the lecture, which is the argument against quantum computers, and it had 3 parts. The first part says that probability distribution described robustly by NISQ devices can be described by low-degree polynomials, LDP. And LDP distribution represent a very low-level computational complexity class. So for those who are familiar with computational class, it's well inside classical AC0, which is bounded depth computation. It's even much more primitive than bounded depth classical computation. And bounded depth classical computation, again, if you're not familiar with these terms, just hear it as a pleasant story. But bounded depth classical computation is it's so low that we can actually prove that it is incapable of making interesting computation. And the second ingredient is in the NISQ regime, asymptotically low-level computation device cannot lead to superior computation. So the second claim is that this computational complexity insight is relevant to real-life behavior. And the third ingredient is that achieving quantum supremacy is easier than achieving quantum error correcting codes. And good quantum error correcting codes are not supported by this very low computational class LDP that was identified by Kindler and me. And therefore, NISQ circuits do not support quantum error correction. And I should say, there is strong theoretical evidence for part A, and there is strong empirical and theoretical evidence for part C, which is actually, I think, in consensus also among believers in quantum computers. And I think part B is the part where most of the disagreement remains. So here's a cartoon I had based on this argument. So what about all the efforts of Google and IBM and Microsoft and Intel, Alibaba, Rigetti, D-Wave, and many groups in...
Excuse me, Professor Kalai, your slide is not changing.
My slide is not changing. Wait. Now?
No.
Okay, so let me try to stop share and share again.
Yeah.
Okay. Oh, here I see Yossi Rinot, my co-author is here. So if you will say hi, this will be with open camera. This will be a genuine. Here is Yossi. So this Yossi is really in Jerusalem right now. Let me share the screen again. Do you see it?
Yeah. Now.
Okay. Let me try to move it back and forth slowly.
Yeah.
Okay.
Absolutely.
Okay.
I think go to the previous slide.
Yeah, this was my previous slide with that. Oh, you didn't see this slide as well?
Yeah. No, this one. Yeah, go to the previous one. Further previous. Yeah, we were only viewing this one. So we didn't see afterward. So we didn't see this one.
Okay, this is an important slide. This is the argument, my argument against quantum computers. Let me repeat it. Probability distribution described by NISQ devices can be described by low-degree polynomial, LDP. LDP is a very low-level computational complexity class, which is well inside bounded depth computation, classical bounded depth computation. The second ingredient in the NISQ regime, asymptotically low-level computation device cannot lead to superior computation. So another way to say this computational restriction restricts the ability of engineers to lower the level of noise, to lower the rate of noise in principle. This gives an in-principle reason why engineers will not be able to lower the level of noise for NISQ systems, because this will allow primitive computation device to make a sophisticated computation. And the third ingredient, which, as I said, is accepted, is that achieving quantum supremacy is easier than achieving quantum error correction. And the quantum error correction is also not supported by this very low-level computational class, and therefore NISQ circuits do not support quantum error correction. And this means that you will not be able to build the building block needed for quantum computation. And you can ask, what about the efforts of Google, IBM, Microsoft? Now, do you see now the cartoon? Intel, Alibaba, many academic groups, including the one I mentioned in China and in Europe and in many countries all over the world. What will happen to their effort to reach very stable qubits and demonstrate quantum supremacy? So my theory predicts that they will all fail. And I even said that you can see the footnote that we should not even expect false positive for high quality encoded qubit. For quantum supremacy, I thought that false positive might be possible. I was not sure. I gave it a 50-50 chance. And in my view, we now witness false positive claims of quantum supremacy, for example, by the Google team. So let me go a little bit to the technicality of my argument. And this is my work with Guy Kindler on noisy boson sampling. So we consider the model of boson sampling. So usually you start with a Gaussian random matrix and apply boson sampling, or you apply the boson sampling, and the claim is that this gives you a distribution which is hard to create by classical computer. And we consider a form of noise where we average the original matrix by a small Gaussian perturbation. So we take square root of 1 minus t times a plus square root of t times g, where g is a complex Gaussian and another matrix. This is matrix of noise, and t is the rate of noise. And now comes the basic mathematical tool, a Fourier tool. We expand the outcomes in terms of a Hermite polynomial. And the effect of the noise, what we showed, is the effect of the noise is that the Hermite polynomial decay exponentially in terms, the coefficient decay exponentially in terms of the degrees. And the nice thing that happened is that the Fourier Hermite expansion for the boson sampling model is beautiful and very simple. It's not trivial, it's interesting, and it's possible to analyze it. And this leads to theorems that I will not state. The first theorem says that when the noise level is constant, distribution given by noisy boson sampling are well approximated by low degree Fourier Hermite expansion. Consequently, this distribution can approximated by bounded depth polynomial size circuits. And they have therefore polynomial time algorithms to perform. The second theorem said that when the noise level is larger than 1 over n, so it's much wider range of noise, noisy boson sampling is very sensitive to noise with vanishing correlation between the noisy distribution and the ideal distribution. So here is the picture. You know, when we talk about boson sampling versus fermion sampling, in the ideal world, there is a huge difference between them. But when we add noise, you see this yellow, this time the yellow little circle is bounded depth computation, classical bounded depth computation. And when we add noise, both fermion sampling and boson sampling are shrink tremendously into these two regions inside this gray complexity class that Kindler and I identified, which is a small part of bounded depth classical computation. And this led to the following conjecture so our noise model was mathematically oriented, and we also dealt with boson sampling. But far-reaching conjecture is that both theorems of Guy Kindler and myself extend to all NISQ systems, in particular to noisy quantum circuits that Google and IBM and many other tried build, and to all realistic forms of noise. And therefore, probability distribution described by mixed system in general can be described by low degree polynomial. This leads to two predictions from this theorem and the conjecture. And again, I will just briefly tell it to you in words. When the noise level is constant, you should expect that robust samples, robust probability distribution are very primitive computationally. And when you reduce the noise a little bit, you should expect that the distribution will be unstationary and chaotic. So the resulting distribution will strongly depend on the properties of the noise. You will run the computer twice, you will get entirely different distribution. So these are the two predictions. Again, here is the picture. Let me skip it. And let me also skip the course of the debate now. In any case, the course of the debate is whether these insights from computational complexity are meaningful for analyzing the ability of engineers to reduce the rate of noise. I claim that they are meaningful, and they imply that engineers will not be able to reduce the rate of noise, and believers in quantum computers claim that they are not meaningful. And you know, the society, humankind spend a few billions of dollars, or maybe tens of billions of dollars to tell who is right and who is wrong. And we should expect an answer in the years to come. And now I can mention another connection, another way that these Fourier methods can be implemented. This reflects my current research with my co-authors. And the theory tells us that samples based on mixed systems, Fourier distribution decay exponentially with the degree. And if we don't witness this behavior, this is something we might be able to test statistically in the data, although it's computationally very costly. And either this, if we will not witness it, either this will indicate a new remarkable phenomenon in quantum physics, or perhaps more likely, it will indicate a familiar phenomenon of a biased data selection that, or some sort of non-kosher optimization that affected the outcome. Okay, so now we come to the last part, and I have only very few minutes, which is what are the underlying principles and consequences from a world devoid of quantum computers, or from the failure of quantum computation. And following the tradition to using cats for quantum thought experiments, let's consider an ordinary living cat. And in a world devoid of quantum computers, we can say few things about this living cat. And I should say, this conclusion applies not only to living cats, but also to very simple realistic quantum evolution and states described by quantum circuits like Sycamore with 10 or 20 qubits. So what can we say about cats? It will be impossible to teleport the cat. It will be impossible to reverse the time in the life of the cat. It will be impossible to implement the cat on very different geometry. It will be impossible to superpose the lives of two distinct cats. Some people are very excited from the possibility of superposing two minds. This will not be possible. And the life of this cat cannot be predicted in principle. And here, as I said, our cat, it can apply to a real living cat, but also it can apply to states that the IBM quantum computer or the Sycamore quantum computer create with 10 to 20 qubits. I should say that human imagination allow you to implement a cat on a very different geometry, And here is a sweet picture by Louis Wain, a painter that devoted his life to paint cats, that change in different periods of his life. And you can look it up. You can look him up. Okay, now we come to the last part, which is predictability and free will. And here, I don't have much time. I will only give you some hints, and I can refer you to my recent blog post on this matter, and also to a paper that I wrote in Hebrew. I hope there will be some English version later. Probably there will be changes, and so this is after many decades. I wrote an academic paper in Hebrew and in philosophy. So I hope it will be accepted well. And here is a small taste of my argument regarding predictability and free will. We compare 12 qubit computer like the Sycamore. So even if Sycamore is not useful to demonstrate quantum supremacy, and I expect that it's not useful to genuinely demonstrate quantum supremacy, it can still help us to analyze the notions of predictability and free will. And my first claim is that the samples of the Sycamore computer with 12 qubits cannot be predicted. And even much more so, Alice's decisions, Alice's brain. And this, in philosophical language, this tells you there is no epistemic determination. We cannot predict the future, or in principle even. But we need to move forward to say that there is no ontological determinism. And here the argument is that certain future events are not part of the past and future causal fabric. And this is explained in the paper. And this leads you to the conclusion that the notion, both for Sycamore and for Alice, the notion, the precise notion which tell you, which allow to, for which you can tell the future, are physically meaningless. And the correct notions are emergent. And this is both for Sycamore and Alice. And for this emergent notion, so Sycamore will not have a free will, but Alice, our intuitive description of Alice is relevant for the correct physical notion of Alice. And with this description, our notion of how the physical, how the flow of thoughts and the decision and hesitations and choices is really reflect the only relevant physical notion for Alice. So let me just show you one picture which shows that even for 12 qubits, this is the samples from the Sycamore experiment are non-stationary, and perhaps they are even chaotic. To show chaos, it's a tricky statistical issue, but we have clear indications they are not stationary. We compared the distribution of the first 250,000 samples from the last 250,000 samples, and we considered the L2 distance, and we showed that if we compared this distance, which is here represented by the black line, to a distance obtained when we randomly split the 500,000 to 2 equal parts, which is represented by the green histogram, we show that it's significantly higher. So this shows that it's non-stationary, and I think there are also some indications that already with 12 qubits, the distributions are chaotic. Okay, maybe I'll just say one word about this slide. Just two things, two recent news. They are even not really recent news in general. The recent news for me, a friend of mine, Or Satat, asked me, what about quantum advantage in terms of quantum key distribution? As you know, there is a famous proposal for quantum key distribution by Bennett and Broussard. and go back to work of Weisner, and it seems that even this proposal, this proposal is mainly useful if quantum computers can be built, and then our usual quantum key distributions are not useful. But some recent work by René and Renner and Bernstein and others that I learned about them recently following Or-Satat question, show that without quantum fault tolerance, these systems are not secure. And this means that in a world, the world of quantum computers, which is the world I expect we live in, this quantum key distribution don't offer security. Another thing which is not such a big news, but for me it was interesting, that in a debate which took place 9 years ago, two quantum theorists, Harrow and Flamia, they wrote a paper and refuted the conjecture that I made, conjecture C. But now there are some reason to think, although well, anyway, I will not get into it, but now there are reason to think that their counterexample is not correct. Okay, so let me come to the conclusion. Understanding noisy quantum systems and potentially even the failure of quantum computers is related to the fascinating mathematics of noise stability and noise sensitivity and its connections to the theory of computing. Exploiting this avenue may have important implications to various areas of quantum physics. And while failing to factor many-digit number, we may gain some insight on the problems that we are thinking from ancient time. We'll probably continue to think for many years on predictability and freedom. So, Toda Rabba, thank you very much. I want to thank my co-authors that I mentioned in the talk, and the many universities and academic institutions and the bodies that host me and support my work. And it's again a pleasure to be here, and I'm very happy to hear your questions. And thank you very much.
Thank you, Professor Kalai. First of all, there are a few questions in the chat box.
Okay, I just opened the chat box. Wait, let me go. Okay. Okay, this is a great question. Okay, let me go to the second question, because the second question is the basic problem with NISQ devices that the noise level is too large or that the noise is correlated in some way. This is a very important question, because for the first 8 years that I studied this problem, I mainly studied correlation, and but I should say the main problem is that the noise level is too large. It is also part of the picture that the noise is correlated, and the correlation requires to reach a lower bar. And if my theory is correct, then this correlation is also correct from inherent reason. You cannot get rid of it, but the basic problem is noise level. The basic problem is that the noise level is too large. And let me move to the first question. Can you explain in what sense you can emergentism? Okay, I should say that the concept that our notions are emergent notions, and this explain various things, including the free will apparent problem. This is a well-known explanation, and and what I say is that, first of all, there is no alternative to the emergent concept. the intuitive concept that we have about Alice and also about the 12 it simply does not make sense physically from the point of view of physics. And the second ingredient, that this explanation does not hold only for such a complicated system like Alice, but also for a 12-qubit quantum computer. So even for a 12-qubit quantum computer, the notion that allow us to predict its behavior, and when I say predict, even just probabilistically, this notion does not have a physical meaning. Only the emergent notion has a physical meaning, and this, for Sycamore, this is related to the general picture, which does not allow quantum computers. So this is the notion, and there is one good question you can ask, which is why the Sycamore itself is not a device that predicts its future evolution. And the answer is precisely because its behavior is chaotic. This means that it doesn't give you any robust description of the future evolution. So this is really a taste of the issue about emergentism, but in any case, it supports the large body of philosophy writing and also some physicists that claim that the emergent notions is a key or is large part of an answer to this problem. And now there is a third question. Okay, or maybe, oh no, okay. So these are the two, oh, sorry. What are your remarks about P-Shaw factorization? Yes, I would, yes. Peter Shaw, in my view, of course, this is it's our picture of computational complexity is highly conjectural. We have a large array of conjecture, and the fact that factoring is difficult is by itself not at all. It's a conjecture which is in some sense much stronger than the NP not equal to P conjecture. And there are famous mathematicians who believe that one day factoring, classical factoring algorithm will be developed, efficient. I don't share this view, but theoretically, I think that factoring give you what's called supremacy, and certainly this is the reality now. So we don't only talk about ideal thing, about what we can do now. So now we certainly cannot factor numbers to their integer components, and I think this is generally the situation, and yeah. So this is my answer to this question. But I should say one nice thing about Boson sampling and about the work of Aronson and Akipov and other groups is that they show that even there are more convincing computational complexity sense for which quantum computers can go beyond classical computers. Thank you for your talk. Can LDP argument be a... Okay, so I don't... Okay, now the next question relates to the MIP star equal RE result. So this is the result that was achieved by a group of researchers, and it's a amazing theoretical result which has a very nice consequences to conjectures in mathematics. And the question is, can the LDP argument be applied to MIP star equal RE to come with a practical version of the result? Well, I think most experts don't expect a practical version of the MIP star equal RE result, but I'm well, certainly we don't expect a device that will solve undecidable problem, but you never know. I think PCP result in PCP theory, which is the classical analog of this development, people didn't expect it to be practical, and actually there are some practical applications, maybe to currency, to cryptocurrency. So I think the MIP star equal RE light show algorithm show you how beautiful quantum computation is and how remote it is from reality. So our job is both to explore the theoretical beauty of quantum computation, quantum computers, and to explore why our world is devoid of quantum computers and this is not relevant. So this is what I can say about, but I'm glad that this beautiful result was mentioned. So Gibran, could you comment on whether we will have any advantage of quantum chemical simulation in these devices compared to the best approximation done? Yes. Okay, this is also a good question, and I can comment that we probably will not have any advantage. Indeed, chemical simulation, I don't expect advantage. I would say chemical simulation, algorithm for chemical simulation, they use types of approximation which are perhaps similar to what I'm trying to do. I don't expect that quantum devices will have practical usage, even in simulating other quantum molecules. I think digital computers will be your best shot. What these devices can buy you is they can enhance your intuition about how to use classical computers and how to build useful classical algorithms. But although this does not contradict my general theory, I would not expect this. Okay, Toda Rabba. There was another comment from Israel that it was interesting. Thank you. How close can we get to a quantum computer? Okay, so this was a question. How close can we get to quantum computers, and say if such computer exists, how does it affect AI encrypted systems? Well, if quantum computer exists, this will have a devastating effect on all the crypto public key cryptography. At least when you ask me, my prediction is that quantum computers will not be built because it's impossible in principle to build them, and the quantum devices, which are very interesting quantum physics experiments, do not offer you any computational opportunities. They are very primitive quantum computational system from the computational complexity point of view. And I should say one part of the theory is to indeed to explain why classical computer is supported by the noisy quantum world, but I will not get to that. Okay. Thank you. Views about superdeterminism with hidden variables. Well, this is a question about, so I don't have views about, there are several tangential areas that I avoided over the years. One is the different interpretation of quantum mechanics, which usually I use. I was educated by a colleague of mine, Greg Kuperberg, but this is tendency of mathematicians. So I really like the the mathematical formalism, and I don't worry too much about interpretation of quantum mechanics, and also not about the debates which go beyond quantum mechanics. So to the question of Nakib, I'm unfortunately not knowledgeable enough to have any views about this matter. And yeah, this is the end of the chat talk. Thank you for your question.
Thank you, Professor Kalai, and it was a wonderful talk. And we really thank you for accepting our invitation, and thank you everyone for being here. And I hope that in future, so my question is a little bit personal to you, Professor Kalai. So a few years ago, you was working with matrix theory. You were building theories regarding to enumerative combinatorics. How did you find interest in completely working on these fronts? So because I don't see any discrete combinatorial structure what you was dealing few years ago.
Oh, okay. So let me explain that. So I worked a lot about combinatorial geometry and convex polytopes, and I think there was in 1988 with Nati Linnell and Jeff Kahn, we worked on influence of Boolean functions. So this is where we introduced this Fourier method and hypercontractivity. So this brought me into this topic. And then there were several subsequent work which get me closer to at least some statistical physics model, especially the work with Itai and Oded on noise sensitivity and noise stability that from 1999. So my interest in quantum computers came from my interest on the noise, and my feeling, first of all, that the skeptical approach is not sufficiently developed, but also that our theory of noise sensitivity and noise stability could be used. And so it's like the saying that when you something about if you're a hammer, you think that everything is a nail. Yes. So I thought, and actually what happened is that the first 8 years, although the motivation came from my work on noise stability and noise sensitivity, I didn't use this theory. So I didn't acted like this proverb that if you're a hammer, you regard everything as a nail. And now when I think about it, it's actually, if you are a hammer, you should think that everything is a nail, because in hindsight, putting our theory and the Fourier method into play was fruitful. I'm also happy about my previous insight on this theory, but this was a fruitful insight. I should mention that I mentioned the work by the group. I mentioned the group from USTC about Boson sampling, and my work with Guy Kindler have led directly to a quick classical algorithm to make samples like the samples they do. So it's still under debate whether it's as good as what they achieve or not, but it's certainly already in our paper for 2014 gave directly a classical algorithm, so it allows spoofing their claim. And also it turns out that although our model was mathematically oriented, it turns out that the model as it is fits a very nice physical interpretation of noise on the interferometer, and the phenomena, the larger phenomena, applies to other forms of noise. So I can say that there were some connections, and I also have some skeptical tendency. As I said, I had some experience in skeptically studying some statistical claims, and this I also didn't expect to come into play, but now with the Google data, so some similar, but you know, so mathematical life are sort of adventure, and you go
Yeah. And
probably.
and are there any connection of the recent work of Lavache and Victorson for which they got the Abel Prize? So on this particular front?
I think both Latsi Lovash and Avi Vigdor's own work had some connection with quantum. Okay, so there are plenty of connection. I can give a new lecture about it. So both Avi and Latsi, both Lovas and Vigdor's own work was important in the so-called interactive proof story, which is a major a story in classical computational complexity, and it is related to the MIP equal RE star that was mentioned. And I think both of them have some works related to quantum computing, because you know quantum computing is a fascinating mathematical notion that many people try to work on. I think Lovas has a famous paper about the Shannon capacity of the pentagon, and he introduced, if you remember, he introduced the theta invariant.
Yeah.
And it turns out more recently that in recent years that the theta invariant, which actually remarkably is also can be computed efficiently, is related to physics. So this is another connection. So I would say, yeah. So the quantum computation fits very nicely with quantum with the theory of computing, and the theory of computing fits very nicely with combinatorics and discrete mathematics. So so all these things are.
Thank you. I think there is one more question, which is by Michael Daikonov.
Michelle. Hi, Michelle. Oh, I didn't. Oh, yeah. This is the question that I said that I don't have views because these notions are unfamiliar. Are familiar to me, but I hope to. Oh, okay, the set of n qubits is covered to the n continuous parameter. It will never be. Okay, there is a remark. I should say that Michel Diakonov is a famous quantum physicist, and he also belonged to the small cozy, also with Robert Alinsky, a small cozy group of people who are skeptical about the feasibility of quantum computers. He wrote several papers about it, and here is I think this is actually he comments that the state of quantum computer is described by 2 to the n continuous parameter. It will never be possible to have them all under control, and I agree. But my 15 years of work can be described as trying to put this statement on mathematical ground, which are related to computational complexity and to the counter intuition that many people.
Oh, at this end, I hope there are no more questions. And thank you very much, Professor Kalai, for a wonderful talk. We really enjoyed it. And I will share the link of the recording of this talk with you, and it will be available on our webpage. So it's time to thank you once again. It's time for sharing the next upcoming, let me just share the next seminar, which is going to be, okay, I think I have lost it. Oh, no, it is here.
Okay, thank you, everybody.
Thank you. Here's the upcoming seminar by Lukas Schimmer. So he's going to talk about variational principle in mathematical physics. So again, something related to physics, and there are a few connections. Okay, mathematics and physics on the upcoming talk on the on next week. Till then, again, first of all, again, thanks to Professor Gil Kalai for a wonderful talk, and I hope that we will be having more talks from you and on more on quantum computing in upcoming time. Thank you, everyone. Thank you.
Goodbye.
Bye bye. Take care.